Probably the most significant addition to At-Risk 6.0 is its new set of time series tools. These allow you to fit time series processes to time series data, and they enable you to define time series processes as inputs for a simulation. These new tools are analogous to the existing distribution fitting and define distributions tools. Just as the distribution fitting tool lets you fit a distribution to a column of data, the time series fit and batch fit tools let you fit one or more time series processes to one or more columns of time series data. Similarly, just as the define distributions tool lets you choose a distribution for an uncertain input, the time series define tool lets you choose a time series process for a set of time series forecasts. Fit. The time series fit tool is used to fit a time series process to a single time series variable. The example illustrated here is of the monthly Dow Jones Industrial Average since 1990. Note that the time series data often has a date column at the left. Although it is not absolutely necessary, it is useful to separate this date column from the time series column or columns with a blank column. You certainly don't want to fit the date column, and this blank column decreases the chances that you inadvertently include the date column in the data range to be fitted. To fit the Dow data, select any cell in column D and select Fit from the time series dropdown on the at-risk ribbon. This leads to the dialog box you see here. It shows a graph of the series and graphs of two important related quantities, the autocorrelation function, or ACF, and the partial autocorrelation function, PACF. These are useful for identifying the type of time series you have. The theory behind fitting assumes that your time series is stationary. This means that its mean and variance are constant through time. It also means that there shouldn't be any seasonality. Often these assumptions are violated. For example, you can see that except for two downturns, the Dow has been trending upward. It is definitely not stationary. Therefore, the original Dow series cannot be fit directly. It must first be transformed to make it stationary. The middle left section of the dialog box helps you do this. You can check any of the options, such as detrend, to induce stationarity, or you can click the Auto Detect button to have At-Risk do it for you. When you click the Auto Detect button, the dialog box changes, as you see here. Now a logarithmic transformation is performed to stabilize the variance, and first-order differences are taken to get rid of the trend. As you can see, the resulting series in red is essentially noise now. And the ACF and PACF graphs have also changed considerably. The transform series is now ready for fitting. At this point, you can click the Fit button directly, or you can click the Series to Fit tab. It shows all of the candidate processes in At-Risk's time series collection. These include autoregressive and moving average processes, Brownian motion and variations of it, and autoregressive conditional heteroscedasticity processes. As in the gallery of distributions you see in the Define Distributions window, you can check or uncheck as many of these as you like. At-Risk will try fitting each of the checked ones to the given time series. Now I will click Fit. Here are the results. For each of the checked processes that make sense for this particular time series, At-Risk finds the best fitting member, such as the best MA1 process, and it ranks these according to a fitting criterion. In this example, it uses the AIC criterion. For the Dow series, the moving average process of order 1, MA1, using the parameters above the graph, right here, provides the best fit. You can see its projection into the future in the right section of the graph. The legend helps explain this. The 4 buttons at the bottom left provide more options. The left 2 are the usual Help button and the Edit and Export button. The 3rd button is for synchronizing. Instead of having the forecasts start after the last historical observation, you can have them start at the beginning of the historical data, as shown here. You are essentially forecasting known values as well as future values. Finally, the 4th button is for animation. When it is toggled on, you see a series of red random sample paths in the graph. If you want to generate future forecasts in your worksheet, you can click the Write to Cells button and then specify a range. For example, the forecasts here are for the next 12 months. These forecasts are live. At-Risk enters an array formula in the specified range that contains the risk MA1 function with the parameters you just saw. You can see it is an array function because it has the curly brackets around it. And that array function is in this whole range. Because this is entered as an array formula, it works as a unit. For example, you can't delete the contents of a single cell in the range. You would have to delete them all. As usual with at-risk distributions, static values appear in the range unless you toggle the at-risk dice button to random. Then they jump around. These future forecasts can now be used as inputs to an at-risk simulation, just like any other input distributions are used. Batch fit. The time series dropdown also has a batch fit item. This enables you to fit multiple related time series all at once. This not only saves time, but it has the extra benefit that it estimates correlations between the time series. The data shown here of monthly bond yields of AAA and BAA bonds can be used to illustrate the batch fit tool. To fit both series at once, select any cell in column D or E and select Batch Fit from the Time Series dropdown. This brings up the dialog box you see here. Again, the date column has been separated from the time series data by a blank column, so at-risk guesses correctly that the data range is in columns D and E. It doesn't include the date. The issue of stationarity still applies, but now it is trickier because multiple time series are involved. One transformation might be required for one time series, and another transformation might be required for another. If you manually check the transformation options, such as the logarithm transformation, your choices will be applied to each of the time series. Therefore, it is usually better to check the auto detect option. At-risk will then try to find the best transformation, if any, for each time series separately. If you use this option, you don't see the transformations selected in this dialog box, but they are shown in later results. For this dataset, you see this message when you check the auto detect option. As it indicates, no set of transformations can be found to make the variance stationary. This sometimes happens, usually because of large swings in some part of the series. In this case, you can click OK and hope that the fit will still be adequate. The Series to Fit tab is the same as before, but now there is a Report tab. It provides several options, including the important option of estimating correlations between the time series. I will place the results in the active workbook. Once you click the Fit button, the main results are placed on a time series fit summary sheet shown here. The top part shows the best fitting processes, MA1 and again MA1, and starting in the function row, There are again live array formulas for future forecasts. Again, the curly brackets for array functions. As before, these can be used as inputs to a simulation. The bottom section shows the correlation matrix, which is an argument in the array formulas. There's RiskCormat. If you check the first option in the Report tab, you also get a separate worksheet for each time series, showing the details of the fits for each candidate process. Define and results. If you use the time series tools to generate forecasts for use as inputs in a simulation, you will probably do it as explained so far. That is, you will probably fit processes to historical data and then use future forecasts from the best fitting process as simulation inputs. However, if you have a sufficient understanding of the various processes, you can choose one directly for a simulation by using the time series define tool. Again, remember how the define distributions tool works. You choose a distribution, such as the triangular distribution, along with values of its parameters, for use as an input cell. In the same way, you use the time series define tool to choose a time series process, along with values of its parameters, for use as a time series input range. To use this tool, select Define from the time series dropdown. This brings up the dialog box you see here. Then you choose one of the processes, such as AR1, and click the Select Series button to bring up the next dialog box. Here you can supply a name, a range where you want the forecasts to be placed, and the parameters of the AR1 process. It is not as straightforward to choose these parameters as, say, the parameters of a normal distribution. You have to have some understanding of the various time series processes. The at-risk help provides some explanations of these processes, but you should still have some background in time series theory before you use this define tool. The forecasts are then generated in the requested range, such as you see here. They then become inputs to a typical at-risk simulation. In this case, the goal is to find the distribution of the total procurement cost over the next 24 months. Again, a live array formula is entered for the prices, and usual, that is non-time series, at-risk distributions can be entered elsewhere, such as for the units produced. I'll now run the simulation. Besides the usual at-risk results, you can click Results from the time series dropdown to get a report like this one. This is in addition to any of the other usual at-risk reports for simulation results. You can experiment with the buttons at the bottom of the window to show information about the time series data generated during the simulation. For example, now I am seeing overlays of the time series prices that were generated during the different iterations.